Hi, welcome to the first video lesson for GCSE Computer Science. Hopefully over the course of these lessons we're going to go through the basics of the specification. We'll go through each subject in turn, we'll have a look at the key terms that we need to remember, the key concepts that we need to become familiar with, and then after these lessons there'll be a series of tests, questions from past papers you can have a go at to see how much of these lessons you've actually understood. If of course you find those tests difficult, challenging, you can go back, watch the lesson again and have another go. In this first lesson we're going to have a look at the CPU, what the actual CPU is and what's actually going on inside the CPU. Now according to the specification we need to be able to describe the purpose of the CPU and we need to have an understanding of this thing that we call the von Neumann architecture. First thing to point out obviously is probably what a CPU looks like. Take a look at the picture on the board here. We've got a motherboard, which is this thing here. We've got a CPU socket, and then the CPU is this thing here that's being fitted inside of that socket. Those of you slightly familiar with computer science may have heard of things like Intel processors, i3 processors, i5, i7. Inside your mobile phone, you've got something called an AMD based processor, or an ARM based processor, sorry, correction there. What we're going to do in this session is actually have a look at what's going on inside that processor and the processor's relationship to RAM, main memory. First thing then, we need to define what we actually mean by CPU. The letters CPU actually stand for Central Processing Unit, and sometimes we abbreviate this to processor. Although, as we'll discover if we go on to A-level computer science, the processor and the CPU slightly different things. But it's okay at GCSE level to refer to the CPU as the processor. The CPU's basic job, and it's a very boring job, is to simply fetch, decode and execute instructions from main memory. And that's all the CPU ever does. It just repeats that fetch, decode, execute cycle. Fetch an instruction from main memory, decode the instruction, in other words, work out what the instruction is asking you to do, and then execute, carry out that instruction. And everything that goes on inside your computer is generally controlled by the CPU. So if you like, we can view the CPU as the computer's brain. Now that's a nice analogy, but I probably wouldn't refer to the CPU as the computer's brain in the exam. Try and remember, the CPU's job is to fetch, decode, execute instructions from main memory, and to control all the tasks that the CPU, that the computer actually does. So, just to clarify, we can view this whole thing as a cycle. The CPU fetches the instruction, decodes it, works out what the instruction requires it to do, and then it executes the instruction. Fetch, decode, execute. That's all the CPU is ever doing. So, within this fetch, decode, execute cycle, we've got a relationship that exists between what we call secondary storage. That's something like your hard drive that stores all the data and programs that you might ever want to use on the computer. And that hard drive, that secondary storage, will be saving, storing programs and files that you very rarely use. It's high capacity, meaning it stores a lot of data. It keeps that data even when the computer is switched off. And typically on a computer, when you go to File and Save, you're saving to secondary storage, and that's normally the hard drive. Main memory is another type of storage, but it stores the programs and the data that you are currently using. Well, the key thing about main memory is it's what we call volatile. When you switch the computer off, whatever is stored in main memory, RAM, will disappear. And that's why frequently in lessons, of course, we'll tell you to save, because you're saving to secondary storage, your hard drive, so that you can come back next lesson and that data is still there. And then we've got the CPU, which fetches the instructions from main memory, which you've loaded in normally from secondary storage. this is another nice way that we could sort of visualize the relationship between the CPU, main memory, and secondary storage. So here we've got a picture of a hard drive with the top taken off. When we go down to the Start menu, and the Start menu on our computer lists all the programs that are available to us, those programs have been installed and saved on the hard drive. When we go to the Start menu, and for instance we click on Microsoft Word, what the computer then does is it takes the program that is Microsoft Word, the instructions that make up that program, and it transfers them from the hard drive into main memory. Because remember, main memory stores the programs and data that we are currently using. So now that Word, our word processor, is in main memory, the CPU can fetch the instructions that describe how Word functions, what happens on your computer screen when you click certain options in Word, and it can execute those instructions from main memory. So, let's take a little bit of a more deeper look at what we mean by main memory. Typically a modern computer these days will have between 4 and 8 gigabytes of main memory. And the more main memory that your computer has, the smoother your computer will run. The better it will be at running more than one program at the same time, something we call multitasking. And if we were to kind of view main memory, we could sort of vision it as a street, a row of houses. And each house has an address, just like a house has a number, and inside each of those houses, each side of those memory addresses could be either an instruction or a piece of data. Now, we can change the program that's stored in main memory simply by going to that Start menu, loading a different program, and we can turn our computer from, say, a word processor into a spreadsheet. We can load a different program into main memory, and we can turn it into a video game. And this idea that we can load different programs into main memory, change the program in main memory, make the computer be something else, is what we call the von Neumann architecture. Sometimes we'll also hear this referred to as the stored program concept. It was invented by an American mathematician. We'll learn a little bit more about von Neumann at the end of this video. So just to clarify here then, von Neumann architecture or stored program concept. A calculator is not a stored program. It's not a stored program computer simply because a calculator can only ever be a calculator. It can't be anything else. Whereas like a smartphone is a von Neumann machine, uses a stored program concept because you can simply turn the smartphone into a word processor by clicking the word processor icon, turn it into a calendar by clicking the calendar icon and loading the calendar program, turn it into a video game by clicking the video game icon, and it loads the video game program into main memory. So, we're going to now delve into the details of how the actual CPU works. But in order to do that, we're going to need to define a few more key terms. These key terms will crop up as we look at what these components do inside the CPU. First thing we need to define is this thing which we call a register. Now a register is just a small storage area inside the CPU. And at any one time, a register can only hold one piece of data or one instruction. And the CPU will have several different registers, each register having a different purpose. The first register we've got is something called the program counter. Now the program counter simply keeps track of where the next instruction is in main memory. And each time we fetch an instruction, we'll then increment the program counter so it keeps track of where the next instruction will be in memory. The memory address register, clue kind of in the name, stores the address that we're going to access, which memory location we're going to get the instruction from, or which memory location we're going to get a piece of data from. The memory data register, that's going to store the actual data that we're passing to and from memory. and in the accumulator, that will store the result of any calculations that we carry out. But it's important to remember that each of these registers can only hold one value at a time. But because they're inside the CPU can get very, very quick access to what's inside these registers. Data then moves about the system between the different components, between the processor and main memory, using what we call buzzies. Now, if you would take the top of a PC, you'd see lots of tiny wires. Those tiny wires, they are the buzzies. We've got an address bus, which carries the memory locations, the data bus, which carries the actual data, and the control bus, which carries what we call command signals. We'll see how all these things fit together on the next series of slides. So, what we have here is a diagram representing the registers inside the CPU. The program counter, here abbreviated to PC, memory address register, MAR, memory data register, MDR, and then the accumulator, we've abbreviated to AC. We've then got the buzzies, which connect the CPU to our main memory, our RAM. Address bus, control bus, and data bus. Inside our main memory over here, we've got a simple program loaded. Now, don't worry so much about what these commands mean. We're going to explain them. First command here is in memory address 1, LDA7. LDA7 says load into the accumulator whatever value is in memory location 7. So this instruction will ultimately cause 3 to get loaded into the accumulator. The next instruction says add into the accumulator whatever is in memory address 8. So this will result in 2 getting added to that 3 in the accumulator. So we'll get 5. Final instruction says store the contents of the accumulator in memory location 9. So that 5 that we got into the accumulator will then get placed into memory location 9. So this program here is simply going to add 3 to 2 and store the result in memory location 9. So let's see how the fetch execute cycle causes that to happen. So, the first step, we need to load the program counter with the memory address of the first instruction. In this case, the memory address of the first instruction is 1. Remember, program counter keeps track of the memory address of the next instruction. And here the instruction is in memory location 1. So we're going to load the program counter with that value. So step 2, we now need to get into the CPU the instruction that's in memory location 1. So we copy that value into the memory address register. We can then place that value on the address bus and put a memory read signal on the control bus. So we want to read in whatever is in address location 1 in memory. So, the contents of memory location 1 is LDA7. We're doing a read, so LDA7 goes onto the data bus and gets transferred into the memory data register, now that we've read that value in. At this stage, we've fetched the instruction. We've completed the fetch part of the cycle. So we increment, add, to the program counter so it's pointing to the next instruction. So now we've done the fetch part of the cycle, the instruction's ready and waiting there, we now need to decode and execute that instruction. So it's a load into the accumulator instruction. So we want to load into the accumulator whatever value is in memory location 7. So we place 7 into the memory address register. Now that it's in the memory address register, we can place that onto the address bus, put the read signal onto the control bus, and we're ready to get in to the memory data register the value that's in location 7. So, what value is in location 7? It's 3. So that goes onto the data bus, and it can come into the memory data register. Because the instruction was load into the accumulator, we can then place that value into the accumulator. So, load the contents of memory location 7, which was 3. That's now in the accumulator. So we've now finished decoding and executing the first instruction. Because it's the fetch, decode, execute cycle, we then repeat this whole process again. So, let's fetch the next instruction. So program counter points to the next instruction, which is in memory location 2. So we put that into the memory address register, read in the instruction that's in location 2, into the memory data register, and we're now ready to decode and execute that instruction. Notice we've incremented the program counter. We need to read in the value that's in memory address 8, which is 2, into the memory data register. Because the instruction is add, we can then add that to the accumulator. So we've now got 5 sat in the accumulator. We've fetched, decoded, and executed the second instruction. Fetch the next instruction. So 3 gets copied from the program counter into the memory address register. Let's read in the instruction that's in memory address 3 into the memory data register. We're now ready to decode and execute that instruction. So the instruction wants us to store the contents of the accumulator in memory location 9. So we need to place 9 in the memory address register. We're doing a write instruction, and then we're going to copy the contents of the accumulator, which is 5, into memory location 9. So we end up with 5 in memory location 9. We've added those two numbers together. Now that might sound overly complex. My advice is to go back in the video, re-watch that part of the video again to see if you can get your head around it. It'll take several attempts before you understand what's going on. So this might be a good point to rewind the video back to the beginning of this section, watch it again, see if you can make sense of it. Okay? So, let's summarize the key points. CPU. Its purpose, its function, is to fetch, decode, and execute instructions from main memory. It's a cycle, and that's all the CPU is ever doing. Fetching, decoding, executing. Fetching, decoding, and executing. Main memory stores two different types of things. You can either have data in main memory, or you can have instructions in main memory. And it stores the data and the instructions that you are currently using. Really important that you use that word currently. The von Neumann architecture is this idea that you can store your programs and your data in the same memory. And because your programs and data are in the same memory, it gives you this stored program concept, where the program and the data is stored in main memory. You can change the program in main memory to make the computer do something different. You want your computer to be a word processor, you load your word processing program. You want your computer to be a spreadsheet, you load your spreadsheet program into main memory. You want your computer to be a video games machine, you load a video games program into main memory. This idea that you can change the program in main memory to turn your computer into something different. Obviously, we need to make sure that we have an understanding of what we mean by a register being a small storage area inside the CPU. We need to know the function of each of the different registers. Program counter stores the address of the next instruction. Memory address register stores the location you're accessing in main memory. Memory data register stores the data that you're transferring to and from memory. And the accumulator stores the results of any calculations. You add two numbers together, the answer will be stored in the accumulator. And then you may move that value back into main memory. And finally, thought you might like to know a little bit of trivia about John von Neumann. He was a Hungarian, emigrated over to America. During the Second World War, he worked on the Manhattan Project, which was the project that developed the atomic bomb for the Americans, which they then dropped on Nagasaki and Hiroshima. He also had some rather outlandish ideas, one of which is von Neumann had this idea that you might be able to create self-replicating machines that could build other machines. And that might be one way in which we could build things like bases on the moon. We could send these self-replicating machines up in rockets to the moon. They would build the moon base, which we humans would then be able to go up and use. So he might be an interesting guy that you might want to look up and learn a little bit more about. And that brings this session to an end. Obviously, suggest perhaps you go back, you rewatch the video. Anything that was in red is likely to be something that you're going to need to remember. So it might make sense to go through your book, make notes on those key concepts to make sure that you're able to define those terms using those key words that were in red. Those will be the words, the terms the examiner will be looking for when he marks your paper in the summer. That's the end of this lesson. Thank you for watching.